Good morning and welcome to all the physics teachers joining us today online and in person at Hawthorn campus. A special welcome to those with the red lanyards who are beginning their teaching journey and welcome to those who are visiting us for the first time. As is customary at Swinburne, I'd like to acknowledge the Wurundjeri people of the Kulin Nation, who are the traditional owners of the lands in which our Melbourne campuses are located, and pay my respects to elders past, present and emerging. It's an honour to host your Teachers Conference and to support your professional development efforts. I'm actually overjoyed at today's theme, making a quantum leap with the International Year of Quantum Science and Technology. Quantum rewrites the rules of classical physics and allows us to do things that were, frankly, previously thought impossible. Quantum clocks, quantum communication, quantum computing, quantum sensing, quantum algorithms and quantum technologies. It can feel like we are in a Marvel movie. But this is science fact and not science fiction. And the promises of quantum are simply marvelous. At Swinburne, our mission is to bring people and technology together. By sharing your knowledge and your expertise today, you are helping bring that mission to life. I'd like to thank you for all that you do and wish you a productive and enjoyable conference. I have a little housekeeping to do. One is bringing people and technology together. That is the Wi-Fi today, so please make sure you're using that. You'll be navigating around our campus to a series of workshops. Most of those workshops are occurring either in the ATC building or in the EN building. We have a few student helpers around. You'll notice them in high-vis vests. Don't confuse them with the workers in high-vis vests. If they're wearing a hard hat, that's not our student. They will help you navigate, exiting the building here and turning right. Most of the, I should say, the front entrance of the EN building there, you can get up the escalators. If you're working on your steps, there's stairs to the left. There is 2 sessions in the undergraduate physics lab, which you can enter through that building there in AD. We also have a new virtual reality experience, which is being delivered in the AMDC building. So just outside here, we'll have Diana will pick up those people and walk them across. If you're a little bit late to the party, you can go down to the building and take the lift up to level 8. In the event of an emergency, the assembly area is in the council car park nearest the train station. And after the event, we do encourage you to beat the traffic by relaxing at the Hawthorn pub and going over all the events of today. We are running our physics contact list again, so if you have missed your phone, you can take it out and touch it and use that QR code to register. Thank you for the events team for providing some incentive in terms of gift cards. That allows you to see some of the outreach activities that we run and ways you can engage with us. There is also, I'll wait for the phones to go down because my next slide is another QR code. There we go. All right. And there's a snapshot brochure of all of the activities if you want more detail as well. By the way, my name is Brenton. I'm the department chair here, and it's really great to have you. And thank you once again, Barbara, for bringing everyone. I think that's now fit for you.
Good morning, everybody. Welcome at this early hour on a Friday. Fabulous to see you all here. And a big round of applause, please, for Swinburne University and Professor Hall for so generously hosting us again. For those of you who don't know me, I'm Barbara McKinnon. I'm the president of Big Physics, and I'd really like to shout out right now to all these people who are making this such a wonderful day. We've got a fantastic lineup of teachers sharing their work with each other, which is just wonderful. Do need my glasses so I actually say what I was intending to. I'd like to thank Brenton for acknowledging that we're meeting on the Wurundjeri land today. And I'd like to encourage you to actually make those respects that we all pay a little bit more concrete by taking the opportunity to learn a bit more about including Indigenous knowledge in your physics classrooms. So there's going to be a very special woman here today, Lisa Maloney, who she is running a session, but she'll also be in the exhibitor area at morning tea and lunch. So I really encourage you to go and find her and find out about how to access her resources, because I think that's something that many of us are not really sure how to go about including Indigenous knowledge in our classrooms. And she's a wonderful, wonderful first step. We're really fortunate to have an extremely busy person speaking to us today, Professor Menicucci from RMIT, who's leading the Australian Year of Quantum project. So we're all across the globe celebrating 100 years since the birth of quantum mechanics. Nick Menicucci is passionate about education in schools, and in particular about achieving curriculum change. We all know that change in education is a very slow process, but we're looking at somebody who's very determined to make it happen. One of the catch cries that we have in education is that we're all teachers of literacy now, and language underpins literacy. So I think it's really wonderful today that Nick's going to be talking to us about the language of quantum and why we need it and where it will take us. So over to you.
Not sure if you,
Oh, I just did not, sorry.
not sure if you should be clapping yet. Should wait to see the talk. Hello, and thank you to Vic Physics and Barbara for this invitation. I'm honored by the invitation to speak with you. I really appreciate that all of you have taken time out to be here. How many of you should be teaching right now? Anyone? Okay, wonderful. So I will try to keep this relevant while at the same time showing things that may be a little bit out of scope to broaden your understanding of what quantum is and to hopefully spark some questions and discussions. All right. Oh, I should also say, due to technical difficulties, some of the animations may not work as well. So I am just going to do the best I can. Let's see how this works. Okay. Yep, that should be fun. Okay. So in June of last year, the UN declared 2025 to be, as you heard, the International Year of Quantum Science and Technology. And the official proclamation was on the 7th of June, my birthday. Coincidence? Yeah, no, it's not my birthday now. 7th of June is my birthday. International Year of Quantum Science and Technology. The AIP decided that was too long, so we just call it the Quantum Year. The UN mission for the year is that the year will be observed through activities at all levels aimed at increasing public awareness of the importance of quantum science and applications. Now, the Australian Institute of Physics, in which I have a leadership role, is leading a national effort to celebrate the quantum year. Now, that does not, that's all right, that does not mean that people cannot do their own thing. But what we want to do is do our own events, including hopefully a Nobel laureate tour, as well as some other significant events with respect to education, with respect to careers, and with respect to policy advocacy. So we want to do all of those things. But in addition, we are extremely happy to have people do their own events and to do things either with us or independent of us that we promote to our social networks, to our mailing lists, etc. So I'll be talking more about how you can get involved at the end. But let me tell you how the Australian Institute of Physics sees our involvement in the quantum year. So our particular mission statement for the Australian quantum year is to celebrate 100 years of quantum science and technology and to inspire the next generation to continue the journey of discovery and innovation. So hopefully you see where you can fit in with that. It's the inspiration. And in particular, we want to, well, I'll just get down to here. So our specific objectives are threefold. One, we have an objective around education. So the education piece is to reveal and explain the wonders of quantum science and its impacts on our lives today and into the future. We actually spent quite a bit of time figuring these out to make sure it captured everything that we wanted to do. If you give me just 1 second. Set a time. Okay, good. The second objective is inspiration. So we have education and inspiration. We want to ignite the nation's curiosity about the beauty and promise of the quantum world and inspire people of all backgrounds, that's very important to us and to the UN, of all backgrounds to pursue careers in science and technology. Now you'll notice that this does not just say in quantum. So this is all areas of science and technology. And this is because we recognize, and at least at some level, the federal government and some of the state governments recognize that technology is going to be the next frontier for careers. It's not just going to be based on, as Ed Husick, the Minister for Industry, said, dig it and ship it. We need to diversify our economy. And I think there's a big nationwide push for that. And we want to be a part of that by promoting careers in science and technology. And we want to celebrate. So we want to celebrate the worldwide achievements in quantum science and tech. And we want to spotlight Australia's pioneering leadership in this endeavor. So why 2025? Does anyone know why? Does anyone know why? Any guesses? Yeah. Good, good. 100 years. Does anyone know specifically it's 100 years since what? This man, brilliant. I can see, I'm really glad you're teaching the next generation of scientists, because that is an excellent deduction. Yes, good math skills as well. Okay, so there's this wonderful paper. It's actually almost 25 years old now, but it discusses 100 years of quantum mystery. So why in 2001 were they talking about 100 years if we're talking about it in 2025? Something seems off here. Now, I don't expect you to read all this. I'll zoom in just a moment. But basically what we have, let me just see, I need to do a quick test. All right, I'll put that away. So what we have is, it was the initial discoveries, the initial explanation of some of the basic features of quantum, but without a full understanding. It was just a little shadow, a little glimpse, depending on the metaphor that you prefer to use. But what we're actually celebrating, as I'll get to in a moment, let's zoom in on this. What we're actually celebrating is this cluster of events that happened in the 1920s, in particular, and most importantly, the Schrödinger equation. The Schrödinger equation is the fundamental equation of motion for quantum mechanics. It replaces Newton's laws. It is how quantum physics works, and it allows us to make concrete predictions about quantum phenomena. It is the basis of everything that we do. So in addition, there were other things as well around that time, including Heisenberg uncertainty. There's a flurry of activity in the mid-1920s. I also want to draw your attention to the Schrödinger's cat. How many people have heard of Schrödinger's cat? Wonderful. How many? Did someone just meow? That's excellent. I approve of that. Let's see. How many people have not heard of Schrödinger's cat? Anyone? It's okay if you haven't. Great. So Schrödinger's cat is a thought experiment designed to illustrate the absurdity or the craziness or the weirdness of quantum mechanics. And the idea is that in quantum mechanics, you have something called superposition. And Schrödinger was trying to talk about this, and I'll talk about superposition more later. And so we'll get to exactly what that is. So please don't quote me on what I'm going to say now, because this is now considered an outdated interpretation. So Schrödinger's cat is a cat in a box with a devilish apparatus. It is a vial of poison whose destruction by a hammer is triggered by the decay of an atom. So the atom, over some period of time, is calculated to have a decay probability of 50%. And so the cat is in the box, put in there alive with the poison, with the atom trigger, and the box is closed up. It's hermetically sealed. There's no interaction with the outside world. And according to Schrödinger, after some period of time, when there's a 50% probability that the atom has decayed, the cat is both alive and dead at the same time until you open the box. Now, that gives horrible intuition as to what superposition and really entanglement is. So anyone who's heard about that, I'm going to suggest that we evolve from that interpretation. That's what Schrödinger's cat is. It's a major thought experiment and an important one in the discussions of physics. Also, we had technological innovations. Perhaps the most worldly significant was the atomic bomb. Now, how many people feel uncomfortable talking about atomic bombs? Myself included. Good, you should. This was a destructive, terribly destructive event. It changed the course of history. It changed geopolitics. It was huge, but do you know where it came from? Scientific inquiry. So the curiosity about how the world works and why classical physics was not working led to discoveries in as well as quantum as well as relativity that gave us this incredibly destructive technology. Now that seems like a warning, and it is, and that we shouldn't necessarily pursue this. Now that's the wrong conclusion, because 2 years later, the transistor was invented. And the transistor has completely reshaped every aspect of life through technology, not just geopolitics, not just in destruction, but in creation, in connection, in the microphone that I have now, the slides that we got up on the wall, the phone that you have in your pocket, everything. And that was also an invention that was based on the understanding of quantum mechanics. Now, moving forward, in the 50s, we had different interpretations of quantum mechanics. I'm not going to touch too much on this because this is again controversial, and I want to encourage you to think about quantum in the lowest common denominator, if you will, of interpretations, and to teach students what is the lowest common denominator of interpretations, the least sensational one, but not one that gives them no intuition, something in the middle. And I've been working on this, and there's other scientists that have been working on this. Perhaps some of you have been working on this. And one of the things that we want to do in the quantum year is to, pardon me, is to collect all of those innovations and that expertise and get them in a room together. Obviously, be mindful of your time, and to figure out a way to teach quantum concepts early on in children's lives, as well as to the public. So there's the pilot wave interpretation, which is the idea of non-local influences. So you have faster than light influences that are hidden from view, but nevertheless they are there. You also have the many worlds interpretation. How many people believe or how many people have heard that quantum mechanics implies that there are multiple universes? Wow, that's a lot. How many people believe that that's true? Okay, you may believe it, but that's not what quantum mechanics implies. And that's important to understand. And what I mean by that is there are many interpretations for quantum phenomena, and the many worlds interpretation is one of the most violating of Occam's razor. So let's just keep that in mind. But you can believe it. It is possible to believe it. It's not inconsistent with experiment, but it's perhaps one of the most sensational, and it creates problems in communication. Is that for me?
Yes.
Thank you. Thank you so much. Yes, I was running out. I was trying to. Thank you very much. Wonderful. Okay. And certain interpretations were ruled out in 1964 by Bell's theorem. I don't have time to go through all of this, but I'll touch on some of it. And then there were, thank you very much. There were experiments 18 years later that exclude the classical description of the world. So that's a world with realistic properties and measurements that have no non-locality to them. So we knew that quantum mechanics was weird by this time. It was proven. Einstein didn't like it. He died before this was shown, but it's a fact of reality. Now, this won the Nobel Prize in 2022 for this experiment and a few others that followed up on it. I'm not going to touch on everything, but I will talk about this invention, the laser. It is an amazing invention, as you can see. Wonderful. But I'll get to more laser stuff later. But this was a huge, huge innovation in technology, in lighting, in measurements, in everything. MRIs. I'm sure a lot of you have had an MRI, and I'm sure most of you know someone who has had an MRI, and these have saved countless lives. MRI is extremely important. It was invented in 1973, and we have improvements on it today. Quantum teleportation. How many people have heard of this? Right? Quantum teleportation is one of the craziest inventions of quantum, consequences of quantum theory that is a technological primitive in that it can be used as part of a quantum computation protocol, believe it or not. So it's not something science fiction, it is real, but there's, as with everything in quantum, there's some subtleties. One thing that's not on this list, but I think should be, is Peter Shor's factoring algorithm. How many people have heard of the factoring algorithm by Peter Shor? Almost no one. And yet, this is, okay, a few of you, that's great. And yet, this is the discovery by a man named Peter Shor that a quantum computer, if you could build one that's big enough and error-free, or at least low enough error rate, if you could do that, you could break all of the public key encryption that is used today. Now, at the time, quantum computers were not even really conceived of, but as soon as this happened, guess who woke up? Anyone want to guess? Thank you. Yes, governments woke up around the world, especially the US. They fund a lot of basic science. To my dismay, I moved to the US, I moved from the US to here, and I found that Australia does not fund as much basic science, and they don't have the same philosophy, but the US definitely does, and other governments have caught up since. But this is why we have an explosion in quantum technology today. Because of this algorithm, because of this discovery, that factoring is hard for ordinary computers, but is easy for quantum computers. Because of this discovery, there was a tremendous amount of investment in quantum computing, and that led to other technology that I'll discuss shortly. Quantum is everywhere today. So this is you can take a photo of this if you want. This is the language that we are using within the Australian Institute of Physics, the AIP, to discuss the quantum year and what quantum technology is doing in our lives today. We call this quantum 1.0 because it is the stuff we already have, and it does not involve the detailed control of individual quantum systems, and it does not use things like entanglement. And nevertheless, it's extremely important, and it is a legitimate quantum technology that came out of the discoveries 100 years ago and since. The LEDs that light our homes and our TV screens in the 21st century. You remember those big screens? A lot of you are probably old enough to remember the huge CRTs, and we don't have that anymore. We have flat screens. The lasers that scan our groceries and correct our vision, not the same laser, but nevertheless, they're both laser technology as well as this laser pointer. The microchips at the heart of every smartphone, computer, and modern car. The medical imaging devices that have saved countless lives in the fight against cancer and other diseases. I mentioned the MRI. There's also the CAT scan, CT scan, the PET scan. And I'd love to tell you that a CAT scan is a special type of PET scan, but unfortunately that's not true. The solar panels and batteries that will enable us to live at net zero. So what's next in quantum technology? Well, we have three basic categories of quantum technology 2.0 that have been identified by CSIRO and by every other government agency around the world and business. There are basically three categories. There's computing, which is the driving force of all of this. And this is expected to be a $2.5 billion industry within the next 20 years and to have at least 10,000 jobs. Sensing and measurement, this is much more near term. Computing is quite a ways off. How many people have heard that we're going to have a quantum computer within 3 to 5 years? Yeah, I would say that that's a bit optimistic. Pardon me. I think I just need a bit more water. I would say that's a bit optimistic, and I should put this link. But there is an international survey of quantum computing experts in terms of that talk about when they believe it is likely that we will have a quantum computer. And the consensus, there are some people that think it's sooner, but is understood to be to become a threat to our encryption in about 20 years, which is why new encryption algorithms are being developed today. These are called post-quantum encryption. You'll hear different ideas. I could be eating my words in 3 to 5 years if PsiQuantum makes it happen. It's possible. Sensing and measurement, this is happening now. This is much more near term. Quantum enhanced sensors, quantum enhanced measurements and navigation. And we already have atomic clocks that are incredible, and they power the GPS satellites to make your phone work. with respect to location tracking. We also have quantum communication, and these are all expected to provide thousands of jobs and a multi-billion-dollar industry. Okay, so hang on a minute. I thought no one understands quantum mechanics. How many people have heard this quote? Now, here's a question. How many people believe this quote? Okay, so I would assert that this is false. And the reason we know it's false is an empirical one. Because we know we understand quantum mechanics because we can use it to build technology. So what do we mean by we don't understand quantum mechanics? It can't be that we have no idea what's going on. We have some idea. And I understand it better than the layperson. You understand it better than the layperson, but I probably understand it better than you, no offense. Just because I've been working in that field for 30 years now. Is that true? 20 years. Let's try that again. Yeah, 20 years. Okay, how old am I? Okay, so why does it seem so mysterious? If we understand it, there's in some sense no mystery. So why does it seem mysterious? So hold that thought. We'll get to that. The real question I would like to pose is, how do we translate quantum to everyday English? This is a tough ask because quantum is like a foreign language that has concepts that do not translate. How many people speak a foreign language, a language other than English? Okay, good. So there would be some concepts that you probably say like, yeah, there isn't really a translation because the language doesn't support the concepts that are inherent to the language that you're trying to translate to doesn't support the concepts that are being translated from. And the problem with quantum is that it is the language of nature. It is not the language of human beings. And so the experience of atoms, hard to talk about that, but the way that atoms interact with each other and the rest of the world is very different from the way that we interact with each other and the rest of the world. And that experience or that happening, whatever happens between the atoms is very difficult to translate to our experience because we don't have intuition for it. And that's really important. We want to translate without giving false intuition. This is key because there have been at least two specific things that have been said that I think give horribly false information. And they have created big problems for people like myself when talking to policymakers and to the future generation. So here's an idea. Let's break and rebuild intuition. Because if we need to talk about the concept and we don't have the words for it, let's just give some intuition about the concept. Okay, so I would like to pose to you that the universe is weird. And I use these slides. I just want to check. 9:40 is the end, right? With some questions before that. Okay, great. Thank you. So I would like to suggest to you that the universe is weird. Now, what do I mean by that? Well, I don't mean that this particular person is weird. I don't know. Maybe he is. But that's not what I mean. What I mean, in fact, is that this photo shows things that are not weird. What's going to happen a few seconds later, or really less than a second later? Right, he's going to hit the ground. Right. How do we know that? Sorry? From our experience of gravity. Exactly. So we do not expect him to just fly off into the sky. And we can also tell what happened before. He made a bad life choice. Okay, so he's riding his bike up that ramp, and he's going to have a bad time. Okay, so we understand this. This is all classical physics. This is not weird. This is an example of what is not weird. Let's talk about this cat. Okay, can anyone tell me what's going on here? What's going to happen to this cat? Yeah, he's going to have a bad time. That's right. So another example of a creature that's going to have a bad time. How do we know that? Because of our experience. We have an experience of what cats are like. We have an experience of what countertops are like. And we have an experience of cats trying to jump on things and failing to do so. But what are the underlying assumptions here that we're making? There's an underlying assumption that the cat was there before you took a picture of it. Ever think about that? that the moon is there when you don't look at it? We have that because of our experience with cats and our moon. And that is a very good heuristic for our everyday experience. The other assumption that I'd like to draw your attention to is what is not affecting this picture. Things that are very far away. So what's happening on Alpha Centauri, or in a different galaxy, at the instant this photo is taken, or really any meaningful time before that, is not affecting what is happening right here. That is the principle of locality. So the first one was a principle of realism, that there is a real world with real properties and real identity of things that exists independent of our measurement of it. And the second one is locality, that what happens far away does not affect what's happening here instantaneously, and vice versa. But we know that this cat is about to fail. I know my memes are a bit old, but whatever. Okay. So when I say weird, I mean unexpected or surprising. I don't mean supernatural. I just mean unexpected or surprising. And we form our expectations from our experience, and most aspects of our world are not surprising. Those that are further from our experience are surprising, and quantum theory is included here, as well as quantum computers. I'm not going to tell you how quantum computers work. It's a big translation problem, but I will tell you one way that they don't work in a bit. So let's talk about quantum weirdness. So in the classical or the everyday world, locality, I mentioned this, what happens here doesn't affect what happens there instantaneously. It takes a while by relativity for that influence to propagate. The maximum speed is the speed of light. Realism says that measured properties reveal the real state of affairs underneath. But in the quantum world, you can't have both, which is weird. In the quantum world, you cannot have both, which is very weird. It means that you have to give one of these up. And if you discard realism, then the underlying reality, you may exist. I mean, it's possible to believe that there is a world, but whose properties are not well defined. Like, think of your own ideas about a topic that you've never heard of. I mean, it's hard to do it because you've never really thought about that. If someone asks you in a survey, well, what do you think about topic X? And you're like, oh, I never thought about that. But you give an answer anyway. Was that answer there before you were asked the question? I mean, not really. That's kind of how we can talk about the exist, but you were there and your brain was there. And so we can talk about a world without properties of that world being real before we measure them. If you discard locality, you get spooky action at a distance. And this is what Einstein was objecting to. He wanted both of these. But you have to give up one of them, or both. But you have to. Okay. Just looking at the time, I think this is important. I want to talk about quantum bullshit. And the reason I want to talk about that is because I want to distinguish it from quantum science. So quantum bullshit uses buzzwords beyond their domain of applicability. Like, our minds are entangled, man. It's not true. It's complete rubbish. Claims quantum weirdness in the everyday world. Crystals can heal you. They're quantum. No. Nope. We use quantum crystals. We use crystals in our lasers to do quantum things, but they cannot heal you. That's not how things work. You're not getting vibrations from the crystals. Untestable, dubious, or nonsensical claims. Quantum says consciousness makes the world exist. What the hell does that mean? I mean, there may be a testable formulation of this, but that statement is just bullshit. Here's one that may be controversial. Quantum says all possibilities happen in some universe. It's okay if you believe that all possibilities happen in some universe. Once again, stand up proudly. Who believes that? It's okay if you do. I don't, but who believes that? Nobody? Really? I'm telling you, it's okay if you do believe it. All right, that's fine. But that's not what quantum tells you. It's not required by quantum mechanics that everything happened in some universe. That is one interpretation, but it is not the only one. It is not the one that I believe fits Occam's razor the best. Quantum science, on the other hand, uses jargon accurately and precisely, like our experiment generates the following entangled state. Fine, you know what you're talking about. Agrees that classical physics describe most experiences, like Newton's laws work just fine for cars and bridges. We don't need quantum mechanics to describe the large-scale functioning of cars and bridges. It's totally fine. The coin is definitely heads or tails. I just don't know which. I'm flipping the coin. Yep, absolutely. Precise testable claims that are not obviously wrong. Entanglement cannot be used to signal faster than light. How many people believe that entanglement, or believed before reading this, that entanglement could be used to signal faster than light? Anyone? Okay, a few people did. That's a horrible disservice that the physics community has done to the public, to suggest that entanglement it means that there's an instantaneous effect. It is not true. It's just not true. What about this one? Quantum particles can be in two places at once. How many people have heard this? How many people have heard that quantum bits or qubits can be in 0 or 1 at the same time? It's a form of the same statement. So let's think about what this implies. If it were true, then it would mean that every time you add another qubit, you double the number of quantum computers you have. That's literally what it means. If it's in both states at once, there's a duplication process that's happening. So let's see if that is actually how a quantum particle works. Is this testable? Let's find out. So what I'm talking about here is how we communicate intuition. Because if we try to say that quantum particles are in two places at once, then we are communicating intuition. And the question is it the right intuition? All right, so this is where I'm going to have to do the animations manually, but that's okay. This won't be too hard. So here I have a diagram of a laser. It has a little light that normally goes on when I hit the button to show that a particle has been emitted. That's not going to work on these animations, but that's fine. All you ever see, you don't actually see a photon coming out of this laser. Because it's going this way. That's what's happening. It's going horizontally, so you don't see it. All you see is this particle detector click. So this spits out a single photon, a light particle, and this is a photon detector. And so what happens is I'm just going to circle the detector that clicks to simulate the click. So what's happening is I push the button on the laser, it sends out a photon, and immediately this goes click, click, click. That one at the bottom does not click at all because it's not in the path of the laser. Okay. If I put a mirror here, which one's going to click? The one at the bottom, of course. So if we do that, I hit the button on the laser and I get click, 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 and nothing up there. All right. What if I put a beam splitter here? Well, a beam splitter is just a piece of glass that's been coated to make it half reflecting and half see-through. You have examples of beam splitters all around you, like this storefront window. You can see the outside reflected. We are outside the store. You can see through the window, but you can also see some reflection. This is a beam splitter. It's just not 50-50, but it acts as a beam splitter. Okay, so what about this? What's going to happen here? Anyone want to take a quick guess? Yeah. So that is correct. So half the time this one clicks, half the time this one clicks. Not exactly half because of statistics, but yeah, you get clicks roughly half the time for both of them. But we only ever get one click. This is the important point. We only ever get one click. You never get more than one click. So I would argue that this invalidates and in fact, there is a specific technological way in which this invalidates the and explanation. It is not that we get the particle going here and here, because if we did, we would get more than one click sometimes. And we don't. We get one click. That's it. It is not that the photon is both to the right and going down. It's not. Okay, well, maybe it's either or. That's possible. So, yeah, I mean, it's 50%. That seems to agree with or. You could do that interpretation. So let's build up a more complicated experiment. So here we have a mirror. Managing my time. So here we have a mirror and a beam splitter. And what's going to happen here? How many people think 50% for both detectors? How many people think all to the right? All to the bottom? Okay. And it is indeed 50% for each detector. when you press the button. Same thing happens here because the beam path goes like this and it splits here 50% for both. Okay. Well, what about this? What about this? So the beam splitter, what we saw was that it splits the probability. So instead of going all in one direction, it's 50% here and 50% here. We have two paths, one path that goes like this and then splits, another path that goes like this and then splits, because this one is splitting it as well. But both paths have a probability of 50% for each detector. Any predictions on what's going to happen here? Whichever path it takes, it should be 50% by classical intuition. How many people believe it's going to be 50%? Good. How many people believe it's all going to go to the right? How many people believe it's all going to go down? So 100% of people believe it's 50%. Well, let's see what happens. And again, I just have to simulate it. Click, 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 click. It never goes to the bottom detector. Your classical intuition has been broken, as it should be, because a beam splitter does not simply split into a 50-50 probability. What happens, it's not merely random what happens with the beam splitter. It's not. And this is a wonderful, simple example of how quantum superposition works. So it is not simply here or there. A beam splitter creates a superposition of reflection and transmission. What is a superposition? Well, it's not and. It doesn't create two copies of the photon because you only get one click. That's the wrong explanation. So please stop, if you do, please stop telling your students. I would highly recommend, I shouldn't tell you what to do. That's not appropriate for me. But I will suggest strongly, because it makes my job easier, that you stop telling your students that it's both here and there at the same time, if any of you do that. I was told that when I was in high school, and I never believed it. It was by my English teacher. So anyway, I knew it was crap then, and I discovered it was crap 15 years later. Superposition is also not or. It's not merely random. Superposition is a new quantum way of combining alternatives. It has no translation to everyday English. It has no translation. Now, there are some examples, there are some analogies we can make, but please don't tell people it's and don't tell people it's just one or the other, because that gives terrible intuition. Classical intuition fails, and that's weird. There's a great game that I recommend you all write down. It's just quantumgame.io. Quantumgame.io. The one that I'm showing here, which I can't because it's a video, is it has the exact same setup. You click on this and it actually shows the photon splitting and entirely going toward this rock. Your goal is to make it go here. And the way that you do that is by adding beam splitters and mirrors. So the solution to this is to put another beam splitter here and another mirror here and here so that you have two of these interferometers. So this one bounces along both paths and then it bounces here and goes there. I'm talking about the paths, not the photon. The photon is in a superposition of both paths and then a superposition of both paths here, and then it all goes to that detector. And that's how you win that particular level. Okay, but what about actual teaching? So I realize I'm getting close to the end of my time, but I think it's important that I talk about actual teaching. Now, I teach at the tertiary level, but I teach closer to you guys than a lot of my colleagues because I teach first year. Although these days I'm teaching second year, but it's still the same content I was teaching. So first year students are just out of high school and they've selected physics or related discipline. And so what happens? Well, first year physics students, let's imagine these are them. They're not really, it's just a stock image from RMIT, but let's imagine these are first year physics students. What they want is the cool stuff. They want Schrodinger's cat, quantum theory. This is an illustration of the diabolical experiment. Thought experiment. He didn't actually do it. Thought experiment. And they want space-time curvature. They want general relativity. Some of them want other interesting fields. I mean, I can't think of any because I'm biased. But I'm sure there's lots of students that come in and want this sort of stuff. And what they get is block on an inclined. And that's what they look like. Yeah. Okay, so why does this happen? Well, it happens. So first of all, this is mostly for my colleagues at RMIT, but I'll let you know what we struggle with. That some degrees are like this. You can do the basic classes in any order, and there's very few dependencies. But physics is kind of like this. There are core classes here, and then we build up from there, and the specialist stuff is on top. So the cool stuff is often up here. That's where the quantum and the relativity and all that awesome stuff is. But because the degree is only 3 years, and because students don't get a lot of time with us, and you might be thinking that you could do some of this in your classroom. If you have time, I realize the curriculum is quite restrictive, but if there's time, why can't we put some of it here or earlier in high school? Why can't we put some of the cool stuff there, some of the concepts? So that was my goal in 2016. That was my challenge, teaching quantum physics to first-year physics students. So there's a few options. One, use words. So Einstein talked about spooky action at a distance. We discussed this, and this doesn't work for that. That's fine. And I would say that this is incredibly misleading, and we should not be using it. It gives people the idea that entanglement can be used to send information faster than light. It cannot, it never will. That is not how entanglement works. Quantum particles can be in 2 places at once. And I said literally everyone when trying to talk about quantum. Not literally, but close. In fact, I was at Science Meets Parliament last week, and I met with a geologist, and I hope she doesn't mind, but she was talking about, she was telling her daughter how Santa can deliver all the presents because quantum physics says that Santa can be, I mean, I'm probably embarrassing her, and I'm sorry about that. Because, but it's not her fault. It's the fault of us, the content experts, who have oversimplified it to the point of it being rubbish and getting it into the ether, the universe, that quantum particles are in both 2 places at once. It gives the wrong intuition. It gives you the idea that you're duplicating Santa, and that's how it works. Of course, I mean, the idea of Santa is a whole other issue, but I won't get into that. This is bad intuition. So option 2 is to use numerical mathematics. Remember, we're trying to teach to first-year students, university students, AKA shut up and calculate. This is literally what people have said. When I got the slides for this course, when I took over, it actually said, we're just going to say shut up and calculate, because all that other weird stuff is just, and that's terrible. The students don't like that. It doesn't give any intuition at all. We can build up intuition. So shut up and calculate takes an expression like this. You do not need to know what this is. And it just says, okay, we're just gonna translate it into numbers, into matrices, and we're just gonna kind of do the arithmetic, and we get 1. Isn't that cool? And the students are like, what the hell? So the purported reasoning is that the abstract maths is hard and quantum is non-intuitive. Numerical maths is supposedly easier, but this maths is too hard for first year. Ergo, mathematical quantum can't be taught in first year. What are you gonna do? I mean, that's it. So it was the actual content was delayed till second year. I didn't like that either. So option 3 that I decided to do was to use abstract mathematics. So what in the world does this mean? I'm going to teach you the tiniest amount of quantum mechanics. What in the world is this symbol? It's a new language. It's a new language, but it is content rich. It is content rich when you interpret it properly. This symbol literally means if we measure the particle by sending it through a device oriented along the y-axis, the particle will definitely deflect upward along the y-axis. That's literally what that symbol means. That's a sentence. That's a sentence about a future experiment that we could do with the particle. That's literally what it means. And this is what I teach my students. This symbol, which is just reversed, is the same sentence formulated as a question. If we measured along y, will it be deflected upward? That's a yes or no question. That's information about what will happen. Anyone want to guess? Well, obviously, the answer to this question is yes, if we have that information. So does anyone want to guess what the numerical value of this expression might be if the answer to the question is yes? 1, yes, exactly, that's correct. Wasn't that a lot easier than going through that crappy mathematics that involve complex numbers. It's just not necessary for the basic intuition that we want to get across. Now, there are complex numbers in quantum. We do need to put them in there, but I tried to put them in there in the minimal amount possible. I was trying to teach them the language of quantum mechanics. This is the specialist language. This is actually the symbol. Sorry, let me try that again. This is the formalism that I use in my work as a quantum computing researcher. So I'm teaching them this, and yes, you get a 1. So actually, abstract maths used in cutting-edge quantum research is rich in meaning and intuition. We just need a dictionary. Then mathematical quantum can be taught in first year. Yay! So in 2016, I developed that dictionary, and I used it to teach quantum physics to first-year students, and it didn't work. All right, I realize I'm getting to the end, so I'm just going to summarize this. Most students needed more support to do well. I'm happy to talk more about these details, but I'll just give you a flavor of what I did. Supporting students to learn challenging material. The key was the tutorials. We needed to do student-centered problem-based learning. That was really, really important. We started with very low attendance, tutor just lecturing to the students. Nobody showed up. It was pointless. They didn't get any benefit. They need to work with each other. They need to discuss with each other. They need to not be talked at. They need to be given problems. I'm sure a lot of you already use this in your classes, but this worked. I also found that their calculus was poor, even though we told them they needed calculus, first semester calculus, just basic derivatives and integrals and complex numbers. And so I gave them calculus self-quizzes. I gave them the problem sheet and the answer sheet, and they were supposed to take 10 minutes to just do all of these questions. Now, for some of you, you might be like, oh no, that's terrible. But for people doing a physics degree, this is assumed knowledge. These are actually not difficult problems. And I told them they need to get about 30 right in 10 minutes. And it's important that it be quick because they need to have this in their long-term memory because the rest is hard. This is in their long-term memory because working memory is a limited resource. And there is research in cognitive theory and education that backs this up. Low stakes self-assessment at regular intervals. And I convinced them that they needed to do that. There were several other things that I don't have time to go into, so I'll just show you the learning outcomes. Well, in the quantum assignment, I started in 2016, and the performance was relatively poor. Here's a box plot. It averages below 50. But in the subsequent years, after I introduced the tutorial solutions, the detailed solutions were incredibly important. And calculus quizzes were introduced, they did much better. You can also see the improvement in performance in the calculus quizzes. So just focus on one color, like the green. So in week 1, they did very poorly on the self-quiz. Then I gave them a different one. And by week 10, once they actually had to use the material, they were up to the level where they needed to be, at least a lot of them were. Okay, so the take-home message is that quantum is a language with concepts that have no translation to everyday English. But 1, we can build up intuition from simulations, games, and well-crafted lessons. And I would be very interested for your help on doing this. I do not expect to know what works in each of your classrooms. This is something that the AIP wants to do, is to work with teachers, respecting your time, to figure out how, for those of you who are interested, how you guys can develop curricula that will help your students learn this. And sometimes the mathematical notation, when properly translated, tells a story better than words ever could. So I just have one little pitch, opportunities in 2025. I showed this slide before. This is the International Year of Quantum. We have all of these objectives, and I encourage you to get involved. You can send us your ideas and tell us what's required to make them a reality, and we will help you with that. We have a bit of funding available, not a lot, but we have a bit. We're trying to get more. So register your ideas at this website or just email us. And also, if you have upcoming events, if you have things that you're already doing or that you know about related to quantum or STEM careers or anything within the remit of the quantum year, register and sign up for the email list and check out the calendar. Thank you very much.
Thank you so much, Professor. And I have the privilege of thanking you on behalf of all participants today. It was wonderful as educators for us to hear the impact we can have in the classroom to save our students from future bullshit when we're thinking about the language choices that we make, and also the simulations and activities we can do to ensure that the futures our students will experience, which are quantum, will be ones that are well understood. And Vic Physics is incredibly passionate about partnerships, passionate about building conversations and community from educators across all levels. So your insights, your enthusiasm, and your invitation were certainly appreciated and a wonderful way to start the conference. So a huge thank you on behalf of all educators in the room for your insight and your views today. We are now moving on to our next session. So that is in workshop A. Just be aware there might be a bit of a discrepancy between the name tags and the rooms that are listed on the program. So the program rooms are correct. So just double check that your room matches your program registration that is on your name tag. If not, please refer to the program for the correct room. You can look out for people who are in high vis to be able to move to the correct locations. Most of the smaller ones are out these doors and then to our right. After workshop A, we are coming back here for morning tea and to view our exhibitors. Hope you have a wonderful day, everyone, and please continue to enjoy the conference.